Yeah, it was that fine gun. It was a
Yeah.
So you've been visiting Stuttgart, or?
I had been, yeah.
Yeah, okay.
But mostly personal visits. But,
Oh, okay.
I have some friends there.
Meher, I'm just about to start sharing a session. Is it urgent? Okay.
So 3 minutes, we'll wait for 3 minutes. Is there any echo? No, no. Chandan, you checked with Shovik?
Yes, ma'am.
He's joining?
Shall we start? It seems to be time.
Yeah, it's 2 o'clock. Okay. So welcome everybody to the, just a minute, I think there's an echo. Hello?
Yeah.
Okay. Okay, so welcome everybody to the post-lunch session. So it's a pleasure to invite Professor Narasimhan back to LDMAT for chairing this session. So over to you, ma'am.
Good afternoon, everyone. This session will be on electronic properties of thin films, and there are 3 talks in it. And the first talk is by Shivankar Chakravarti from INST Mohali. And the title of the talk is Planar Hall Effect, Anomalous Hall Effect, Shubnikov-de-Haas Oscillations, Berry Space, Oxide Interfaces with Strong Spin-Orbit Coupling. Over to you.
Yeah, thank you so much. Let me first thanks Sangeeta, especially, and all the organizers for kindly giving us this opportunity to share our very recent works with all of you. So these are the things which we are continuously doing, and many of the part we still don't understand. Is the screen and everything is fine? Am I audible?
Yeah,
everything's fine.
Okay, fine. So we are basically interested in oxide thin films, interfaces, and superlattices. This is an example of kind of interfaces we can grow in our laboratory. This is a TM image of one of our thin film. So the thing starts like this. There are 2 very fundamental pillars of physics. One is special theory of relativity and quantum mechanics, which gives rise to Dirac equation. So this Dirac equation was mainly elusive to high energy physics so far, but recently in condensed matter physics, people have seen Dirac, Weil, and Majorana fermions as a quasi-particle excitation of different material. And people have also seen the related phenomena, which is reflected as non-trivial Berry phase, chiral anomaly, Rashba spin splitted band, and so on. So we especially ask the question, can we realize this fascinating physics in oxide materials? That is what our aim is. So this slide basically represents the overall idea of our research. We are working on a two-dimensional charge carriers in presence of an electric field, which could be internal or external. Now, if these electrons are moving with a relativistic velocity, then at the rest frame of this electron, this electric field basically converts into a magnetic field, giving rise to a fixed quantization which depends on the direction of the motion of the electron. So your spin quantization and the momentum of the electron is now locked to each other. So fortunately, we have several friends within the institute, INST, and within Mohali city at ISR Mohali. And in India, we have collaborators from ISC Bangalore, Bose Institute, and BARC. For few measurement, we also collaborate with internationally at Japan. This whole research is supported by DST Nanomission, PRNS projects, and of course from Institute of Nanoscience and Technology. So today I'm going to talk about from 4 of my students, mainly from Neha's work and Nanch Kumar work. Neha and Ruchi is also going to talk today after my in this same session. Neha and Ruchi was my first PhD student. Neha has moved to Cornell University. Ruchi is now working with Pratap Rai Chaudhary at TIFR. So this slide is specially for my student friend. What is perovskite oxide? It has a general formula of AbO3, where A is an alkaline or rare earth ion and B is a transition metal ion. This is a simple crystal structure where A is sitting at the center of a cube and B sides are sitting at the corner of the cube, and each B atom is surrounded by 6 oxygen atoms. Now the point is, why are you interested in perovskite oxide? This is a fascinating material because it shows almost all possible physical properties, starting from superconductivity, magnetism, ferroelectricity, and so on and so forth. So it covered the whole spectrum of electronic, optical, and magnetic properties. Today, we are especially going to talk about the two-dimensional electron gas formed at the interface of 2 insulating materials, perovskite insulating materials. This is not an entirely new phenomenon. What ingredient we want to incorporate in this is, number 1, we want to incorporate strong spin orbit coupling in this system, and also we want to incorporate magnetic interaction. So basically, you can see these 3 recent publications for the talk I'm going to talk about, for the things I'm going to talk about today. This is a basic idea of the Rashba physics which we are looking at especially for my student friends. So let us start from a free electron model. What is that? You have a p square by 2m type Hamiltonian, and the energy is given by h cross square k square by 2m. So your K versus E diagram looks like a single parabola. Now, instead of having a free electron, if this electron is now moving with a relativistic velocity under an electric field, then what happens? Because of the Lorentz transformation, this electric field is now converted into a magnetic field at the rest frame of the electron. And because of this magnetic field, the spin of this electron is now quantized in a direction defined by the direction of the motion of the electron. So what is the corresponding Hamiltonian? The Hamiltonian is now the free electron minus the magnetic interaction terms. And your energy is no more a single k square like dependence. It has now plus minus k linear dependence. And your single parabola in EK diagram is now split it into 2 parabolas, and instead of having one Fermi surface, it has now two Fermi surface. One is outer Fermi surface and another is inner Fermi surface. And each Fermi surface has a different spin chirality, which means that in K space, the spins are rotating in one direction in this Fermi surface and in other direction in other Fermi surface. Okay, why this kind of system, which is known as Rajba system, are interesting? This has interest from both technological application point of view as well as from the fundamental science point of view. So these are the materials which can be used for spintronic application. By applying electric field, you can now tune the magnetic state of the material and use a off-on state, or you can realize a spin transistor. Now, from the fundamental science point of view, if you now carefully look at the K equal to 0 point or the band crossing point, it has a linear dispersion. So now we have a Dirac cone, and this Dirac cone is now has kind of confined by two different Fermi surface having two different spin chirality. So this era of high mobility electron gas at the interface of two insulating materials started at 2004, when my friend Otomo and Harold has seen the formation of two-dimensional electron gas at the interface of lanthanum aluminate and strontium titanate. Both are insulating, but if you put them together, it forms a two-dimensional electron gas. So this is the resistivity as a temperature, and it goes down, suggesting this interface is conducting. So now we have a paradigm shift where we want to incorporate strong spin orbit coupling in this type of two-dimensional electron gas. What could be a possible choice? One of the possible choice which we thought was potassium tantalate. Why? Long back, it was shown that if you dope potassium tantalate with barium, then it could give rise to a very high mobility electron system, and at low temperature, mobility can even rise to 10 to the power 4 times. And recently in 2012, it was shown from angle resolved photoemission spectroscopy that it has a reasonably strong spin orbit coupling, which is approximately 300 milli-electron volt. Now, let us try to very briefly try to understand what is the origin of this kind of two-dimensional electron gas at the interface of two insulating materials, which is known as polar catastrophe scenario. To understand this, we can say very simply, a perovskite material can be categorized into non-polar and polar type of material. Let us assume that you have a strontium titanate, then each layer, for example, this layer, which has a BO2, titanium +4 and oxygen -4, has a charge neutral layer. The next layer is strontium +2 and oxygen -2. This is also charge neutral layer, and it's known as a non-polar perovskite oxide. But if you think of a lanthanum aluminum oxide, then this layer, BO2 layer, has a -1 charge and AO layer has a +1 charge. So what happens if you put a polar material on the top of a non-polar material? So polar material, this has a charge distribution. Each layer has a positive, negative charge. And due to this, it has a step-like electric field. A step-like electric field gives rise to a diverging potential. But diverging potential is not a very good thing. Nature doesn't allow. So if you start preparing very thick, kind of increase the thickness of this polar film, then this divergence also increases. What is the way to get rid of this divergence? One can send half an electron from the top of the surface of this polar film to the interface, which now gives rise to a zigzag-like electric field, and one can get rid of diverging potential to a converging potential. So how to identify if you have a polar catastrophe? You must have half electron doping per unit cell at the interface, number one. Number two, there should be a critical thickness of the film above which you should see a two-dimensional electron gas formation. Okay. So we are using pulse laser deposition technique for deposition of our sample. So this is the real picture of a pulse laser deposition system which we have in our laboratory. And this system is basically equipped with a very nice technique called reflection high energy electron diffraction system. What you do is the following: you take a substrate, and if you apply an electron beam, and if the surface is very clean, then this electron beam diffracts and forms a very strong diffraction pattern. Now, if you start depositing something on the top of this, the intensity of the diffraction pattern decreases. Once one monolayer of the thin film is deposited, the intensity again goes up. So by exactly counting the number of oscillation, one can exactly say how many monolayer of thin film have you grown. So I will be trying to talk about two materials today. One is lanthanum vanadate thin film, which is an insulator on the top of potassium tantalate substrate, and europium oxide thin film crystal, which is a ferromagnetic insulator on potassium tantalate substrate. So we have grown lanthanum vanadate with different thickness on potassium tantalate substrate, and we can exactly calculate the number of layers by looking into the read intensity oscillation. This is the X-ray diffraction pattern. You can see extremely nice Laue fringes are coming, suggesting that you have a very clean and well-defined interface. And this read intensity oscillation suggests that you have a layer by layer growth in the system. Then we have started performing the temperature dependence resistivity measurement. What we have seen is that number one monolayer thin film of lanthanum vanadate is completely insulating that interface. When you go 2 monolayer, it has some measurable resistivity, but it is insulating. 3 monolayer is kind of conducting, but it is still going up. But above 3 monolayer, all the sample has same resistance. It doesn't depend on the how many monolayer of thin film you are growing. So it suggests that it is not the thin film which is conducting, but rather the interface is conducting. Then you have performed the conventional Hall measurement, and you can see that you have a very linear like Hall data, which suggests that you have a single type charge carrier in the system. From this Hall measurement and resistivity data, we could calculate the charge carrier density and mobility, and you can see the charge carrier density is approximately 3 into 10 to the power 14 per square centimeter, which is actually equivalent to half electron doping at the interface. Now, let me give you a brief comparison of our system with previously reported system. If you see lanthanum aluminate and strontium titanate interface, it has a critical thickness above which the interface become conducting, but the amount of electron doping was much less than half electron doping. Take the example of gadolinium titanate and strontium titanate interface. It has exactly half electron doping, but you don't need a critical thickness to get the interface conducting. But in our case, it satisfies both the scenarios, that you need a critical thickness as well as you have exactly half electron doping. So it says that it is a perfect example of polar catastrophe. Then we have performed the conventional magnetotransport measurement. What we have done, we apply a magnetic field out of plane containing the two-dimensional electron gas, and you measure the longitudinal resistance as a function of magnetic field. And you can see at low magnetic field, there is a sharp increase, suggesting that the existence of weak anti-localization. One can fit this weak anti-localization to figure out the spin orbit coupled magnetic field, and we could see the spin orbit coupled magnetic field is around 4.4 Tesla, which is highest among all perovskites so far reported. Now let me tell you some analogy which actually motivate us for our future measurement. What is that? Think of wire material. What you have 2 Dirac cones, and each Dirac cone is kind of circulated by electrons with 2 different spin chirality. Now, if you look into a Rashba system, it's not exactly same, but it has some similarity, that you have a Dirac cone, and this Dirac cone is circulated by 2 Fermi surface with different chirality. So in case of wild material, this phenomena is reflected as chiral anomaly. The signature of chiral anomaly are negative in-plane magnetic resistance, planar Hall effect, and anisotropic magnetic resistance. So we ask the question, can we see these signatures in our material which is not known as a wild material? So we performed the angular dependence of magnetic resistance. What we have done, you apply a current along x-axis, then you tilt your magnetic field from z direction by an angle theta, and you measure the resistance as a function of magnetic field. So when you apply the magnetic field along z direction, it's completely positive magnetic resistance. But as you go from 0 to 90, that is out of plane to in plane, then you see a positive to negative magnetic resistance transfer. This looks very similar to topological materials. And as you increase the temperature, creeping the magnetic field along the direction of current, then above around 120 Kelvin, it becomes a negative to positive magnetic resistance. Let us see exactly how this has similarities or dissimilarities with topological material. This is our sample. If you rotate the magnetic field from out of plane to in plane, you see a positive to negative magnetic resistance, which was also repeated for wild type material. This is a positive magnetic resistance when it is perpendicular magnetic field and when it is in plane magnetic field. But the dissimilarity comes when we start rotating the magnetic field in the plane of the two deck. So what is the geometry of this measurement? You have sent this XY plane is the two deck plane. Now you send the current along X direction and you apply a magnetic field making an angle phi, and theta is now 0, that is in plane, and you measure the resistance along the direction of current, which is longitudinal resistance and known as anisotropic magnetic resistance. And also we want to measure the perpendicular resistance, which is the planar Hall effect. I'm coming in that in a minute. And we could see that if you change the phi, it never goes from negative to positive magnetic resistance. But in case of wild material, if you apply the magnetic field in plane and change the magnetic field from current direction to away from current, it goes from a negative to positive magnetic resistance. Now, for this out of plane measurement, what we have done, we kept the magnetic field fixed and we changed the theta, and we could see a cos square like dependence, which has a very similarity what we have seen for chiral anomaly system. And also we had seen a formation of plume that is along the direction of the applied magnetic field, which is also very similar to reported chiral anomaly. Now we had also performed what is known as planar Hall effect. What is that? You apply the magnetic field in plane and you measure the transverse resistance or transverse voltage. If we think about our normal Hall effect, then in plane magnetic field should not produce any perpendicular resistance or voltage. But in few materials, especially in magnetic material or in wild type material, because of the chiral anomaly, people had seen the appearance of planar Hall effect. And this planar Hall effect, we have also observed this is the planar Hall effect as a function of the angle between current and applied magnetic field. It oscillates and it has a cos phi sin phi dependence. And if we change the amount of magnetic field, then the periodicity doesn't change. So this is the corresponding contour plot in phi versus magnetic field plane. And there is only two-fold oscillation has been seen. But when we look into the longitudinal magnetic resistance, which is known as the anisotropic magnetic resistance, we could see at low magnetic field, it has a two-fold oscillation. But as we go to the high field, it has a two-fold to four-fold transition. And if you look into this contour plot, you can also see a two-fold to four-fold transition. We had it was reported for wild semi-metals, the planar Hall effect, planar Hall amplitude as a function of applied magnetic field usually follow a B-square like dependence. So we had plotted this B-square like we had plotted this planar Hall amplitude as a function of magnetic field in our system. We could see that in low magnetic field, it has a B-square like dependence, but as you go above 8 Tesla magnetic field, exactly where you have seen a two-fold to four-fold transition, then this B-square like dependence deviates and it becomes a linear type dependence of applied magnetic field. We have tried to give a phenomenological understanding of this observation. What we did is the following. I have 10 minutes, right? Okay. I quickly.
Yeah, you do.
Yeah, I quickly give you an idea what is the possible mechanism we had tried to understand. Let's start from a Hamiltonian which has a Rashba type Hamiltonian, plus this is the applied, this is the Hamiltonian coming, this is the part of the Hamiltonian coming from the applied magnetic field. Now, if you do so, so this is the unperturbed part and this is the perturbation in the system. Now, so there are two frame of reference. One is the rest frame of reference of the laboratory and another is the frame of reference of applied magnetic field. If we now select this applied magnetic field frame of reference, then you have two components. One is the parallel resistance in this frame along the direction of the magnetic resistance, and another is the perpendicular resistance, which is perpendicular to the applied magnetic resistance, which is nothing but the Drude resistance. Now we have to calculate this B parallel. So we had calculated the B parallel by using this transition from K plus to K minus and sandwiched by a Pauli spin matrix, because now spin and momentums are coupled. So instead of going into the detail, when we transform this resistance back from this magnetic field frame of reference to our laboratory frame of reference resistance, then you could see the resistance has a B square dependence as well as has a cos square phi dependence. Maybe if time permits, we'll discuss this in little detail. So we have seen that in low field limit, we could explain our data by using this simple model. But what we could not explain are negative appearance of negative magnetic resistance, this unusual angular dependence of magnetic resistance, doubling of the periodicity in AMR at high field, and deviation from B square dependence at high field. So we have covered lanthanum vanadate potassium tantalate interface. Now I'm going to talk about the another interface, which is europium oxide and potassium tantalate. What is the difference between these two? Both are insulating, but now instead of having a non-magnetic material, you have a ferromagnetic material. So this is an interface of ferromagnetic material. So we had grown this on a one-on-one oriented potassium tantalate, and when you measure the interface conductivity, it is conducting down to 1.8 Kelvin. But for this material, we didn't see a linear Hall. We could see a non-linear Hall. If we now subtract the linear component of the Hall, we could see it looks like as if a anomalous Hall data, but there is always a confusion between anomalous Hall and two-band conduction when you see a non-linearity. So what we did, we had done the temperature dependence of this Hall measurement, and we could figure out that this anomalous part actually vanishes exactly at the TC. This green curve is the magnetization curve as a function of temperature, which has a TC around 79 Kelvin, and this anomalous part of the Hall effect also vanishes around a similar point, which suggests that this signature is actually the anomalous Hall effect. So this is an observation of anomalous Hall, first observation of anomalous Hall effect in a potassium tantalus based system. We were fortunate enough that we could see the quantum oscillation or the Subnikov-Dahas oscillation in our longitudinal magnetic field. What we have seen, we could see that it has two types of oscillation. When we take the Fourier transfer of these two types of oscillation, it gives two peaks. From these two peaks, we could able to calculate the charge carrier density. One Fermi pockets gives rise to 4 into 10 to the power 12 number of carriers, and other gives you 2.7 into 10 to the power 12 number of carriers. Now we want to know the nature of these two Fermi pockets. What is the easiest way is now you rotate your magnetic field and look into the Shubnikov-Dahas oscillation. We could see that once you start rotating the magnetic field away from the perpendicular direction, this oscillation, this small oscillation, which corresponds to smaller Fermi surface, immediately vanishes. Which says,
Shubhankar, you have 5 minutes left.
Yes, I'll be done. So this suggests that these oscillation correspond to the 2D characteristics, and this larger Fermi surface basically correspond to the 3D Fermi surface. So we tried to understand intuitively why it is so, because at the interface you have a quantum well. So the lower lying band should look like a 2D material, or you have a band quantization, but as you go away from this interface, then you have a continuum and you could see the 3D type material, 3D type band structure. So we plotted this intensity of Shubnikov-Dhas oscillation, and we have able to calculate the mass of these two type of carriers, which is around 0.6 of electron mass and 1 of the electron mass. Then we have plotted the fan diagram, Landau fan diagram. From the Landau fan diagram, we have seen something very interesting. We could see that if you extrapolate this Landau fan diagram data, it doesn't go through the origin, suggesting that you have a non-trivial Berry phase in the system. So this is very usual, because if you have a Dirac point and an electron is moving around the Dirac point very near to the Dirac point and complete one circle, then it acquires a Berry phase, which should be a pi Berry phase. So, and in addition, we also seen the appearance of weak antilocalization, suggesting that you have a Rashba type spin splitting. So what we know about this system? We know that this system has a trivial parabolic band with a carrier density 5 × 10⁻13. We have another two bands which are non-trivial, among which one has a 3D type band structure and another has a 2D type band structure. So we now accumulate all this known data, and we could figure out from the solely from a transport measurement that the band structure should look like this, that you have a heavy lighter band which is not Rashba splitted, and this is the majority band, and you have 4 Rashba splitted band, from two of them is kind of participated in the Shubnikov-Dhas oscillations. So what are the open question gives rise from all of our observation? What is the exact band structure of this interface? Do we really have Rashba, or it has Y? What is the explanation of negative magnetoresistance? We also don't understand this unusual angular dependence of magnetoresistance in the system. The explanation of planar Hall magnetoresistance and at the high field is also not known. We also not sure about the topology of this material. Is it trivial type topology or a non-trivial type topology? So we have conclude that we have realized this is a fast realization of two-dimensional electron gas with strong spin orbit coupling. We had shown that this spin orbit coupling has a highest among all perovskite material. We had shown very unusual dependence of magnetoresistance on the angle. We have shown the observation of planar Hall effect and AMR, which has shown in chiral anomaly scenario. And we have also shown the observation of non-trivial Berry phase and signature of Rashba spin-splitted band in an oxide interface. So thank you very much. I would like to just advertise one of my students. This is the pin code of INST written by one of my students by using an atomic force microscopy, and you can see this in this paper. So if you're interested, you can see our recent publications on potassium tantalate, and we are free to discuss because we barely understand most of the things. Thank you very much.
Thank you very much for an excellent talk, very intriguing results, and also thank you for keeping to time. Are there any questions? Maybe you can stop sharing, then we can see the participants and see if they've raised hands.
Can I ask a quick question?
Yeah, sure, please.
Hi.
Hi,
this is Shovik. Great talk. So I was just curious about the 3D band part. So if you do the similar scaling with thickness, do you see a component which does not, which scales with the thickness?
Oh, no. The thing is that if you scale the thickness of the thin film, nothing changes because it is the interface which is conducting.
No, I was curious about when you say there is a 3D band. So I mean that should be like, extended over some distance. And do you see some sort of a scale?
Yes. We have recently performed some spectroscopic study, and you could see that the width of this 2-deck is not really a 2-deck. It has a width around 15 to 20 nanometer beneath this potassium tantalate.
I see.
So if you go, so the idea is that if you stay near the interface, then it's like a 2D type. And if you go a little far from the interface, it is a 3D type.
Okay.
But honestly speaking, we don't know the real band structure.
Okay.
Any other questions? Does anybody else have any question? I don't see any raised hand. I was wondering, have theoretical calculations been done on these materials? Because questions that you have about the band structure and the topology and stuff like that, couldn't they be answered by doing a theoretical calculation?
No, not yet done. Not yet done.
But are you planning to explore these possibilities?
Yeah. We are, but we didn't get anybody in real terms of band structure calculation. So whatever we have done is a phenomenological thing, assuming that you have a Rashba-Spin-Pretest system.
Okay, thank you. I think it would be interesting to look at this because that might clear up some of these open questions.
I just wanted to add one thing. People have seen superconductivity in this system,
Mm-hmm.
and the TC is above 2 Kelvin, which is a very high TC.
Oh, that's interesting.
Uh,
in which system?
In europium oxide KTO, but in when you are preparing this in 111 direction, not in 001. 001 is not superconducting, but 111 is superconducting and magnetic.
Okay. Any other questions? Okay, if not, let's thank Shivankar for an excellent talk. Thank you very much.
Thank you.
Shall I wait for a minute for the next talk or shall I start?
You can start.
Okay, so the next talk is by Shouvik Chatterjee from TIFA Mumbai. And the title of his talk is Controlling Magnetoresistance in Semi-Metals at the Atomic Scale. I'll tell you when 25 minutes are up, okay?
Sure. Is my screen visible?
Yeah, it's visible.
Yes, it is.
All right. Thank you, everyone, and good afternoon to you all. It's really a great pleasure to be a part of this conference, and I'd like to thank the organizer for giving me this opportunity to present some of our work on controlling magnetoresistance in semi-metallic system. So before I start, I just want to take a minute to tell about our group. We are just a very brand new group. We just started late last year at Tata Institute of Fundamental Research in Mumbai, where we are working on many different aspects of quantum materials, particularly epitaxial synthesis of functional intermetallics, magnetotransport, and also electronic spectroscopy techniques. And we are also interested in their application areas of spintronics and also quantum computing. With that, let me start. Today I'll tell you about a particular class of semi-metallic systems, which is that of rare earth mononuclides. And it has a pretty simple crystal structure of that of a rock salt, and where it's a binary compound. You take one element from the rare earth family and one of the detergent, and put it in a rock salt crystal structure. And these material systems are of interest for quite a variety of reasons, particularly for their application areas. These are, has great potential to be used as terahertz polarizers and emitters. People have also been interested in their potential in thermoelectrics and plasmonic devices, particularly long wavelength infrared devices. But another interesting thing about this materials class is that they can be very easily integrated with the 3-5 semiconductors. As I show here, I'm plotting many different lattice parameters for many different rare earth mononuclides, and you can see that they are very well lattice matched to many different kinds of 3-5 semiconductors. So taking advantage of that, we can actually synthesize these materials various nanostructures, quantum dots, one-dimensional wires, in a self-assembled manner. And here I'm showing an example where you have this erbium antimonite, this metallic quantum dot that is embedded in a 3-5 semiconducting matrix. And this has been also been useful to make burrito-homing contacts in 3/5 and also efficient diffusion barrier. But today I'll take a little different track, and I'll talk about the electronic structure in these material systems, particularly the large magnetoresistance that one can observe in these thin films, and also in bulk single crystals. And we'll also evaluate whether there is any role of topology in the band structure that's playing a role in their physical properties. But also keeping in sync with the outlook of this conference, which is about the low-dimensional material systems, which rare earth mononuclide is not. But I'll show you that having access to bottoms-up approach of this material synthesis, we can actually create a quasi two-dimensional material just by dimensionality tuning from this otherwise 3D material systems. And I'll discuss about some of the interesting physical property that can come about in such material systems, particularly the role of the interface and its role in the stabilization of a 2D whole gas that come out from bonding mismatch. Okay, so just starting with magnetoresistance, we just heard a talk about a little bit in related transport phenomena. All of us know that in magnetoresistance, if you think about the semi-classical treatment, you expect at low fields you have a quadratic dependence, and then it saturates at high field values. And generally for metallic systems, it is of the order of few percentages. Now, for the last couple of years, there has been actually a lot of different material systems that has been studied, which shows this very large non-saturating magnetoresistance. And one ready explanation for the emergence of this kind of a property is the electron-hole compensation, where if you have, where you have exactly the same concentration of the electron and hole carriers in your material system, then you can get very large magnetoresistance, which primarily depends on the level of charge compensation, carrier compensation, and also the mobilities of the electron and hole-like carriers. But even more interestingly, what it was pointed out that if you look at this behavior, which one can see in many different kinds of semi-metallic systems, they shows a very similar temperature magnetic field phase diagram, and many of them has been predicted to have a topologically non-trivial property. So there was some curiosity in understanding whether this topological non-trivial nature actually has a role to play in this emergence of this large non-saturating magnetoresistance. So as I, perhaps all of you are very familiar with the concept of topology now in this condensed matter systems. This is basic, and I won't take much time, but just so that we are all on the same page. This is just a new way of classifying matter, which goes beyond the traditional Landau's-Vogel symmetry paradigm, and particularly if you think about the Z2 class, which is relevant for these rare earth mononuclide systems. There you expect a band inversion in the bulk, and that leads to the emergence of a strongly spin-orbit coupled topological surface states that lives in this projected bulk band gap. And particularly in this rare earth mononuclides, this comes about due to a combination of a relativistic correction and the spin-orbit coupling. And that leads to this band inversion between the rare earth T and the Nicktogen P manifold, as is shown here. And you see this band gap here, this inverted gap here, and you expect to have topological surface states. Now, to evaluate the electronic structure in one such compound, so we grew this epitaxial thin films of one such compound belonging to this material class, which is that of lutetium antimony. And we do this by this technique known as molecular beam epitaxy. So for, at the 0th order approximation, you can think of it just as an atomic spray painting. We have this very well calibrated sources from which we are just spraying atoms, and we get on a heated substrate. And we can then grow these materials with atomic precision. So we have a precision of the order of monolith. So we can really grow this compound at the very one atomic layer thickness scale. So here, as it was shown previously, we also can look at the electron diffraction in situ in real time while growing these materials. And I'm showing you some of these diffraction images in here. so what you can see is that we synthesize this material on gallium antimonide because it's well lattice matched, and also nice surface atomic arrangement is ideal. So you can see as we start growing this lutetium antimony, you have immediately 1x1 reconstruction that you should expect from our rock salt crystal structure. And one can also look at a TEM image, and here I'm showing you one such lamella where we are looking along the 110 direction, and you can see this very sharp interfaces, and we also have high quality film without much disorder. So now that we have our thin film, let's look at the electronic structure. And as we are interested in learning about the Fermi surface in this material system, one can do that by looking at the Schütting-Haas oscillations, which I'm showing you here. You can extract the oscillation and do a fast Fourier transform to get the frequencies which correspond to the different Fermi surface pockets that are there in this material system. And here is just a DFT calculation, which tells you that one should expect that at the zone center, you have two hole-like pockets, and at the zone edge, you have a more elliptical electron-like pocket. And just by using Onsager relation, we can actually, from the frequencies, we can extract out the corresponding Fermi wave vectors for these Fermi surface pockets. And that I plotted here. And you can see that we have a very good compensation in these bulk material, in the sense that we have this material in the bulk has almost equal concentration of the electron and hole-like carriers. And from here, we can also get the anisotropy factor for this elliptical electron pocket, which is about 3. So which is basically the ratio between the semi-major and the semi-minor axis of the ellipse. So we can also do this, get information about the electronic structure directly by doing something known as the angle resolved photoemission spectroscopy, which allows us to directly visualize the band structure in a material system. And this is just a twist on the Einstein's photoelectric effect, where what we're doing, we're coming in with a monochromatic light source and kicking a photoelectron out. And now if you can measure this photoelectron's angle at which it is coming out vis-a-vis some well-known crystallographic axis, and also the kinetic energy, then one can do the simple energy and momentum conservation principles and get the desired quantities, that is the binding energy and the in-plane momenta of the electron when it was inside the solid. One catch here is that you need to do it, this is very surface sensitive, so you need to do it in a really ultra-high vacuum chamber, and you have to maintain that pristine sample surface. So we had actually built this some sort of a vacuum suitcase, so you can go from the growth to the measurement chamber, which was here, it was done in Berkeley at that fast light source. So when we do that correct, we get a direct visualization of the electronic structure, as I'm showing you here. Again, there is no surprises. So what I'm showing you in this picture here is basically a cut through this three-dimensional Brillouin zone, where the cut is a planar cut which goes through the bulk gamma point. And as you can see, we have two hole pockets near the bulk gamma, and you also have this electron pocket at the zone edge. And from here again, we can also extract the Fermi wave vectors. And on the right, what I'm showing here is that if you take a cut along this direction and you plot the binding energy, or the spectral map, the spectral intensity as a function of binding energy, where the in-plane is the in-plane momenta along the two different directions, which is the gamma x is along this direction. We can take a cut along this direction, or we can take a cut along the gamma k, which is along that direction. And we see that it matches very well with the density functional theory calculations. And the same for the electron-like pocket, as I'm showing you here. So the upshot here is that, so we can establish that there is this material system is completely topologically trivial. There is no influence of topology in the band structure, and it agrees very well with the density function theory calculations, which shows that the magnetoresistance behavior is primarily dictated by the electron hole compensation that we find in these material systems. So now the next question is, can we actually play games with this material platform that we have and actually try to tune some of the properties that can emerge in these materials? And we start doing that by growing films of different thicknesses, which is again a design choice. So just by going from a 40 to a 6 monolayer film, we actually have a transition from a 3D to a quasi 2D material system, and we see a very dramatic change both in magnetoresistance and also the Hall behavior. So I just want to point out a few things here about the Hall resistance. So let's just plot just the two different thicknesses, and you can see that in the thicker film, we have a clear multi-carrier Hall behavior, which when you go thinner, it becomes single linear, single carrier Hall-like behavior. And furthermore, if I go very thin film, which is 8 and 6 monolayer, there is a change in sign in the sense that it goes from the electron-like to the hole-like Hall's behavior in this material system. So the question is, can we understand all these things that we see in our magnetic transport? So, because we have this direct eye on the electronic structure, so let's look at how we see how the band structure actually changes as we grow thinner and thinner films. So one thing that I just want to point out, that one thing that you would expect in this thinner films is the emergence of this quantized levels, which is the quantum well states, just because we are now sampling the KZ in some finite values because of the finite thickness of these very thin films, which depends on the thickness of your actual thin film. And now, if we do this for many different thicknesses, what we find are two things. And so here, again, I'm showing you this cut, which is along the gamma m bar direction. So this is the surface Brillouin zone. So along the gamma m bar direction, going through the gamma point, which is shown in here. As you can see, this hole-like pockets are actually the Fermi wave vectors is actually going down as you go down in the film thickness. But if you do the same thing for the electron-like pocket at the zone edge, we are taking this cut here, as I'm showing you here, there is not much difference, okay? So what you immediately can conclude from here is that though in the bulk limit, we had the equal concentration of the electron and hole-like carriers, as we go thinner and thinner, we have more and more electron-like carriers than the hole-like carriers, and that explains going from the multiband to a single electron-dominated linear Hall behavior in a 20 monolayer thick film. But that does not explain why we have change in sign from the negative to the positive, unless there is a big change in the mobility values as we go thinner between the electron and the hole-like carriers. We can also do things a little more quantitatively here. So here I'm showing you this extract on this plot. I'm showing you the extracted Fermi wave vectors for different Fermi surface pockets. And we also try to match it with the density functional theory calculations, where now we do a slab calculations. But we find that we can't reproduce the trend of the electron-like carrier, where we did not find much change in the Fermi wave vector. But for the DFT calculations, it's telling us that both the electron and the hole-like carriers, the Fermi wave vector should actually reduce as you go thinner and thinner. So that is one discrepancy we need to sort it out. Before that, you can also get this lifting of the electron hole compensation, this signature of that also in the magnetotransport. We do the same, same sort of calculation, same sort of analysis on your other thin films. So we get Stubnikov-Dehaas for till 20 monolayer thick films, and as you can see that particularly for the hole-like carriers, we have quite a big change, but not for that much for the electron-like carriers. That again establishes the fact that in the ultra thin limit you have more electron-like carriers than the hole-like carriers. But then there are two questions. One is that our slab calculation cannot capture the trend in the electron-like band, as I showed you earlier. And the second is that in the ultra thin limit, our observed hole-like Hall behavior is actually at odds with both the RTES and the DFT calculation. So can we understand that? And to understand that, we have to understand that the thin films that we are talking about is actually not a freestanding layer, but we also have an interface that is between the gallium antimonide and the lutetium antimony layer. So taking that into account, we just make a very simple three-component Drude model where you have contributions from both the electron-like carriers, hole-like carriers, and also an interfacial charge carriers. Okay. And if you look at our data, we can clearly see that we have some interfacial hole-like charge carriers of the order of 10 to the power 14 per centimeter square, which is pretty high. And that turns out to be about 0.8 holes per 2D unit cell. And this 2D unit cell is shown here, which is basically you have one lutetium-1 antimony atom. And another thing here is that if I look at the trend for the thinner film, we can see that the GXX and the GXY over B has actually a T square and the T cube dependence. That tells me that the mobility is actually dependent on the thickness, and that is expected if our mobility or the the mean free path is actually limited by the interfacial scattering, which is again something one would expect for a quasi 2D system. So we went back and tried to do another density functional theory calculations, now taking into account the interface explicitly. And what we find is actually we do have an interfacial band right here, which arises from the gallium s orbitals. So as I'm showing you here, this is basically the hole-like band that emerges, that is an interfacial band. And if you look at the charge density distribution, you find that though it is well distributed in plane, but it is very tightly confined in the out of plane direction that is perpendicular to the interface. And then what one can do is that one can then map out the Fermi surface corresponding to this interfacial hole-like band and calculate the Luttinger volume, which comes out to be 0.7 holes per 2D unit cell per interface. And I must point out that this should be taken as a lower bound because we found that the actual value actually marginally depends on the kind of potential that we use. We use a GGA potential, which is not great, but HSE would be better, but due to this computer, because it becomes computationally very expensive. So we had this GGA, and this should be considered as a lower limit. Now we can expand a little bit further. We can also check the charge density distribution along a direction perpendicular to the interface. And what we find is that there is actually also a charge transfer happening both towards the lutetium antimony and the gallium antimonide layer. And the amount of the charge transfer is about 0.45 electrons per 2D unit cell per interface. And the amount towards the gallium antimonide is very negligible, which is 0.05. And if we plot the density of states, which is the layer, and we do it at a layer resolved manner, what I want to draw your attention to is that if you look at the interfacial layers, you see this contribution from that particular interface states that I was talking about, but you don't see that in the pulp. This is again a confirmation that the band that we're talking about is arising from the interface. Now, we can do it actually, we can get an idea about this interfacial charge in a little different way, which is just a simple exercise in electron counting. And let's think of the gallium antimonide as ionic, in the ionic limit. And in the ionic picture, because you have this bonding mismatch right at the interface, right in here, you're going from a zinc blend to a rock salt structure. What you would expect is that the gallium actually transfers, let's say, 1.5 electrons to both the top and the bottom layer of the neighboring antimony layers. Now, from there, if you have a charge transfer of 0.45 electrons towards the lutetium antimony layer and 0.05 to the gallium antimony, and what you have here is this about 1 electron per 2D unit cell area per interface. Now, if you assuming that this excess electron occupies the interface band, so what we get is a 1 hole per 2D unit cell. But remember, gallium antimonide has a significant covalent character, which will reduce this number, so we can think of this as an upper bound. So from these two, coming from these two directions, one of this Luttinger volume calculation and one from this simple exercise in electron counting, we can put both a lower and upper bound for this 2D whole gas carrier density, which comes out to be between 0.7 and 1 per 2D unit cell area. And from and this matches very well with our experiment, which we find 0.8 from our magnetotransport data. And now, if we understand our argument of this electron counting, and if we assume that we have 0.8 holes per 2D unit cell, that just translates to 0.25 electrons being transferred to our lutetium antimony layer. And now here I'm just showing you, replotting the same data as I just had shown you previous, a few slides back, where I was saying that we are not able to reproduce the trend in our DFT calculation, what we see in the ARPAS data. But now that we understand that there is a charge transfer that is happening, and we know how many charges are there at this interface, so if we add this 0.25 electron into the lutetium antimony bulk, we actually reproduce the trend of the electron pocket as a function of thickness, as we see in our ARPAS measurements. So this gives, again, very good support to our proposal that there is an interfacial charge and the charge transfer that is actually responsible for the observation in our ARPAS measurements. We can go one step further. Actually, if we look at our calculations, because of the same bonding mismatch, what it predicts is that there will be a tiny buckling of these lutetium atoms. So if you look at, in the bulk, it is a classic rock salt structure. So if you go from the lutetium to antimony to lutetium, you have a 90-degree angle. But just at the interface, you will have a buckling, which this is about 93 degrees. So what you would expect is that if you try to actually measure the lutetium to lutetium distance along this atomic column, the first lutetium interatomic distance would be smaller than the rest of the lutetium distance as you go away from the interface. And that actually we can track by directly measuring these distances by using a transmission electron microscopy, and that's what I've shown you here. So where this violet arrow actually represents the distance between the lutetium to lutetium, this lutetium interatomic distance. And so we go along this atomic column, and just for statistics, we integrate over from this area to this area. And this is what I've shown you here. So this is where the interface lies. And this distance is the interatomic distance between the first lutetium to lutetium atoms, and then for the second, for the third, for the fourth, and so on. And if we plot the average lutetium to lutetium distance as it goes away from the interface, we see there is a sharp decrease in this particular lutetium interatomic distance, which you would expect if there is a buckling of the lutetium atom at the interface. Okay.
Souvik, you have 5 minutes left.
Sure. Okay. Yeah. So that again corroborates our whole understanding of what is happening in the system. This is just to show the same thing in a more detailed manner. I won't go into this. But so what I want to highlight is that, as it were in the previous talk, it was pointed out that there are many different ways of having a two-dimensional electron gas in the material system. One is this idea of polar catastrophe, where you have a polar and non-polar interface, and primarily people have seen this in many oxides. Then there is also a way of using electrostatic band bending, which has been very fruitful to get into quantum and fractional quantum Hall effects. And here we think that we have found another way of actually stabilizing to the electron of the whole gas in a material system, which comes primarily from this bonding mismatch. So this is more or less like a chemical route, and it should be ubiquitous in many different material systems. And actually, there are some recent reports that in a similar material system of europium sulfide on a 3,5 semiconductor, where you again have this rock salt and a zinc blend interface, there are these sort of interfacial charges that one has to be cognizant about. Okay. I think I have a few minutes, so I just wanted to say that there is also some idea that in semi-metallic system, as you grow thinner and thinner, you can actually, due to this dimensional confinement, you can actually open up a band gap. So there would be like a semi-metal to a semiconductor transition. So though we have this upturn in resistance, at thinner films, which could be construed as the opening of a bulk band gap, we just show that this is actually due to a combination of electron-electron interaction effect and a weak anti-localization effect. And from here, we can actually see that as you go thinner and thinner, particularly for a 6 monolayer film, it is primarily dominated by your phase coherence length is primarily dominated by electron-electron interaction effect, as opposed to both the contribution from electron-phonon and electron-electron interaction. So with that, I'll just summarize what we have discussed so far, is that we demonstrated that we can synthesize high quality epitaxial thin films of lutetium antimony. In the bulk, though, there is a perfect carrier compensation and similar carrier mobilities, but as we grow thinner, we can actually control the magnetoresistance by changing the carrier compensation as we grow thinner and thinner films. And also there is one has to be careful about the interfaces when you go into this ultra thin regime. And there is a new way one can think about of inducing this interfacial 2D electron or hole gas by taking advantage of the bonding mismatch between two different crystallographic, two different kind of crystal structures. And finally, I hope I've shown you that if you combine a synthesis with some spectroscopy tool, it can be a very powerful to investigate novel electron states of matter. So with that, I'll just stop and ready to take some questions. Thank you.
Thank you very much for an excellent talk. Are there questions? Shavi, can you stop sharing perhaps so that we can see the participants?
Yes. Yeah.
Are there questions? Okay, while people are getting their thoughts together, maybe I'll ask you a question from a theorist perspective. I was wondering about the DFT calculations. Is it sort of hard to do calculations on rare earths, like rare earth materials like this? Is the lutetium a problem? Because of strong correlation effects, and do you have to put a U, Hubbard U? How does one handle that?
Yeah, so in most of the 99% of the cases, that would be true. But lutetium is actually a little more favorable because it has a full F shell.
Okay.
One does not need to worry about too much
Okay.
about the strong correlations. But yes, you're absolutely right that if we go to, for example, some other partially filled F shell, then yes, one needs to take care of add some Hubbard U to take care of the position of the F electron bands. But again, as I was so like we see directly in our electronic structure, we can figure out that whether we have some F orbitals or the bands from the F states near the Fermi level, and whether one needs to take care of that. So we can provide some input to the theorists to what's the level of U it is correct.
And the other question I had, maybe I didn't understand correctly, but to get the agreement between the experiment and the theory, you said you accounted for the charge transfer and then you get the agreement. Right. So do you put that charge transfer in by hand, or can't you just directly take the interface system? Because as I understand, you did the calculation on the interface to get the charge transfer anyway.
Yes. That is true. But as I said, so if you okay, maybe I can share quickly if that's okay. So basically, even the ARPA's data that I showed. Let me just. Yeah. So this ARPA's data that I showed, I mean, this very good agreement. This is not if you use a GGA functional. It actually shows that this particular third band crosses the Fermi level as well. So one needs to do this sort of correction, which is honestly a little black box to me, but you have to use some sort of a HSE, or you have to use this MBJ kind of potential to get the right electronic structure. But then to do that for the slab calculation, it becomes very—
It's just too expensive.
Correct. So then what we do is that we do some sort of a scaling. So that's why we can't directly get, because the numbers kind of vary. So what we took is the other way around, is that, okay, let's say that the experiments are correct. And if the experiment is correct, because from the experiments, we get the value of, 0.8 holes per 2D unit cell. And we put that as a number to back calculate how much with this, electron counting exercise.
Yeah, yeah.
Charges one should get, and then if I put that back in our calculation, it's pleasantly surprising that we see it agrees very well with the artist. So
So did you collaborate with some theorists, or did you do the calculations within your own group?
No. So this was done in collaboration with Anderson Genotti's group at University of Delaware.
Okay. All right. Are there any other questions? Thank you. Are there any other questions?
Can I ask one question?
Yes, please.
Yeah, so Shobik, so this formation of the 2D gas which you're talking about depends a lot on the substrate which you're using, right? Because it's because of the mismatch, if I've understood correctly. Right?
Yeah. So I mean, well, it depends on the substrate in the sense that it depends on the crystal structure of.
Yeah. So you have the mismatch in crystal structure. So you have you tried with some other substrate?
Right. Yeah. So we have not tried, but as I was telling, so it looks like at least for the zinc blend rock salt combination, so we have now another report. It's on archive. I can find and send you. So basically, where again you have, as I was mentioning, between indium antimonite. So people are trying to do this, Majoranas, and so either you want a ferromagnetic insulator. So European sulfide is a good example, and you put it on a 3,5 indium antimony nanowires. So they're finding these sort of interfacial effects. So that is probably another, just another experimental data point. But I think it should be the same thing should work in many other systems as well. But yeah, we have not. I mean,
but the mismatch in crystal structure is required.
Correct. Yeah. At least from this route, for this chemical route that we are.
Yeah.
So you need to see a mismatch in crystal structure, but a match in lattice constants.
Well, the match
to get the epitaxial growth, I guess, right?
Yeah, just for us to grow. I mean, we can incorporate, lattice mismatch of 2-3% percentages.
Okay.
It will just train, but that will just probably change the numbers a little bit. But this phenomena should still hold. And whether if, for example, another area we are interested in, because particularly for optoelectronics and all, lead selenide, this is again similar things. People are trying to grow this lead selenide on 3,5s. And again, the thing is you go from a zinc blend to a rock salt. So that could be another interesting avenue to look for whether we can stabilize similar behavior. Yeah, but they can accommodate this lattice, this bonding mismatch a little better. So it will be curious to see how this thing pans out there.
Any other questions? Okay, if not, let's thank Shobik again for an excellent talk. If you want, you can put on your mics and clap. Okay, thank you very much. Okay, so we can go to the last talk in this session. It's by Ruchi Tomar, and the title is Emergent Phenomena at Oxide Interface.
Ruchi, you're muted. Ruchi, you're muted. You have to unmute yourself.
You have to go to full screen, and you also have to unmute yourself.
Yeah. So I hope I'm audible and my presentation is in full screen.
Can you talk a little bit louder, perhaps?
Yeah. Is it okay?
Yeah.
Thank you, Professor Shobna. And good afternoon to everyone. I am Ruchi Tomar. I have recently joined TIFR. The work which I will be discussing here is from my PhD from Institute of Nanoscience and Technology, Mohali, with Professor Swankar Chakravarti. So in INST Mohali, I will work on the oxide thin films, interfaces, and superlattices, and we study their transport, magnetotransport, and magnetic properties. These are my collaborators, national and international. So I would like to thank them for their scientific discussion and help in some of the experiment and theoretical simulations. Lastly, I would like to thank Department of Science and Technology for their funding support. I am also very much thankful to the first speaker of this session for introducing these oxide material and discussing their interesting properties observed in them and in detail. So what I would like to emphasize here that as mentioned by him, these oxide material which are insulating in nature, they host two-dimensional electron gas at their interface. And the mechanism for this conductivity is the electronic reconstruction, which is the transfer of half an electron volt per unit cell to the interface, and then interface become conducting. But this electronic reconstruction mechanism has been challenged by proposing a number of other mechanisms, including oxygen vacancies, cationic intermixing, and cationic stoichiometry. Despite being unfolding many interesting properties such as magnetism, superconductivity, quantum oscillation, and so on, still the mechanism for this two-dimensional conductivity at the interface has been in debate. So I have tried to look into into this. And for that, I chose the heterostructures of lanthanum aluminate and strontium titanate because first, the lattice mismatch between these two materials are very low, which is less than 0.4%. And another an interesting main advantage of these heterostructure is that their growth condition is rather reducing as compared to LAOSTU heterostructure, which is also discussed by Hota and his group. And one of the major advantage here is that this vanadium has less oxygen affinity than aluminium. So there is always a less possibility of creation of oxygen vacancies at the interface of lanthanum aluminate and strontium titanate as compared to this lanthanum aluminate and strontium titanate. Which is the main concern in the oxide heterostructures. So these heterostructures of lanthanum valentate and strontium titanate, which will be termed as LDO-STU, has been grown by employing pulsed laser deposition system in our laboratory. And these are the deposition parameter which has been optimized to grow these kind of heterostructure. So I'll not go into the more detail of the growth. So what I would like to emphasize here, the key result is, as you can see here in the resistivity versus temperature graph, only the films which are lanthanum deficient, they are metallic, and the films which are near to the stoichiometry or lanthanum rich, they are insulating in nature. So just by changing the cationic film stoichiometry by less than 1%, it can turn the metallic interface into insulating. And this is the charge carrier density graph as a function of film stoichiometry, which also shows that that the charge carrier density in these heterostructures are nearly equal to 3.2 into 10 to the power 14 centimeter minus 2, which is expected from the electronic reconstruction mechanism. So the takeaway message from here is that the electronic reconstruction as well as film cationic stoichiometry plays an important role for creating the conducting interfaces of these insulating material and are the reason behind the conductivity. So the phenomena I am more interested in today's talk is the planar Hall effect and anisotropy magnetoresistance, which has discussed by the first speaker of this session also, that these phenomena are the oscillation in the transverse and longitudinal magnetoresistance, and their origin can be different. So usually these material can be seen in the ferromagnetic material or the topological material, where in ferromagnetic material, the origin of this oscillation is the interaction between the charge transport and the magnetization. And in case of topological material, the origin is the chiral anomaly, as also discussed by yesterday in one of the yesterday's talk by Karthik Raman, Professor Karthik Raman. So this kind of phenomena also observed in oxide heterostructures and were found to be sensitive to applied magnetic field, temperature, and electrostatic gating. As you can see here, on decreasing the magnetic field or increasing the temperature, these four-fold oscillation turn into two-fold oscillations, and at some particular magnetic field and temperature value, they just disappear. Whereas the similar has been observed for 110 interface of lanthanum aluminate and strontium titanate, and the origin of these phenomena are different. In 001 case, the interaction between the conduction electron with the localized magnetic moment which are associated with the crystalline symmetry was the reason, and for 110 case, the change in the Fermi surface due to the orbital configuration and reconstruction was the reason for such kind of phenomena observed in this heterostructure. So I took as a reference for these two papers and try to explore whether LVO-STO heterostructure also hosts such interesting phenomena or what is new. So by taking the motivation from here, I grew 8 monolayers of LVO film on STO with different orientation, that is 001 and 111. So here is the schematic showing the layer formation for both the interfaces and the charges present in each layer. So as you can see here from the sheet resistivity versus temperature graph, both the heterostructure shows metallic behavior down to low temperature. Then we moved on to magnetotransport measurement. Then in first measurement, we performed out of plane measurement, and here we applied magnetic field perpendicular to the plane of the current, and we measured transverse and longitudinal magnetoresistance. So these are just the conventional hole measurement. So the linear behavior of this graph for both the heterostructure and the negative slope shows that we have one type of charge carrier, that is electron in our system, and these are the longitudinal magnetoresistance. Both the heterostructure shows positive magnetoresistance, and in case of 111 LVO-STO heterostructure, we see signature of the weak anti-localization, which is signature of the spin orbit coupling in the system. Then in another measurement, we apply magnetic field in plane of the current, and we measure their transport property at low temperature of 1.8 Kelvin and with 14 Tesla magnetic field. And we have observed oscillation in both the directions, longitudinal as well as transverse. So in the longitudinal magnetoresistance, we see 4-fold and 6-fold oscillation for 001 and 111 heterostructure respectively, whereas the transverse magnetoresistance in both the cases shows 2-fold symmetry. Then we did the detailed analysis of this AMR and THE on changing the magnetic field, and we have changed magnetic field from 14 Tesla to 0 Tesla. And we see that on decreasing the magnetic field in both the heterostructure, the AMR amplitude decreases, and as you must be remember, in case of LAO-STO, these 4-fold oscillation from at high magnetic field transform into the 2-fold oscillation. But here in case of LVO-STO 001, no transformation from 4-fold to 2-fold oscillation has been seen. Even at magnetic field of 1 Tesla, we could see a 4-fold oscillation. Whereas in case of 111 heterostructure, similar to LAO-STO, the 6-fold oscillation transform into 2-fold oscillation, and just below 5 Tesla, the oscillation disappears. Then we have plotted the percentage change in AMR as a function of magnetic field for both the heterostructures, and we see higher change in AMR in the 001 heterostructure as compared to 111 heterostructure. So which is the highest among whatever the reported oxide heterostructures are. We also observed the decrease in the PHE amplitude on decreasing the magnetic field. So similar to the AMR observed for 001, here we could see oscillation up to 1 Tesla in PHE also. But in case of 111, similar to AMR, the oscillation just disappear below 5 Tesla. Then we explored the effect of temperature on the AMR and pH for both the heterostructure, and we see that on increasing the temperature, these oscillations just die out due to emergence of thermal fluctuations at high temperature. And we see here, sorry, so we see here that on increasing the temperature, in case of 001, the oscillation persists around 100 Kelvin or 150 Kelvin, whereas in case of 111, the oscillation in AMR or PHE, they just disappear above 50 Kelvin. So high.
Ruchi, you have 4 minutes left, okay?
Yeah, sure, ma'am, I'll be done. So we try to investigate the origin behind these kind of phenomena, and we see that we do not see any signature of magnetic ordering in our system, because as you remember, the whole was quite linear. If the magnetic ordering was the reason behind this, so we could have seen anomalous Hall effect, but we do not see any kind of magnetic ordering in our system. So we perform theoretical simulation for both the heterostructure. So these are the density of plot for, and this is the Fermi level, which is also showing the metallic nature of the heterostructure. Here in this, we have shown the DOS projected onto 3D orbitals of titanium atoms, and we have shown the contribution from these orbitals, and we have also plotted the contribution from the titanium layers. Here in case of 001, we see that these orbital dyz and dxz, they get hybridized and then gives orbital polarization along z-axis. And then we have also plotted the Fermi surface in case of 001, and we see that the appearance of this open orbit, which causes the four-pole oscillation even at a low magnetic field of 1 Tesla. The similar calculation was done for the 111 heterostructure also. In case of 111, we have this hybridized dyz and dxz orbitals, and the contribution from the hybridized dxz and dx square minus square reduces the contribution from the yz and xz orbital. That is why we get lower AMR in this case. And then this Fermi plots for 001 and 111 shows the 4-pole and 6-pole symmetry, which is the crystal symmetry in 001 and 111 heterostructure. So our theoretical calculations also indicates that in case of LVO-STU, the origin of these oscillations in AMR and PHE are arising from the change in the Fermi surface due to orbital polarization and hybridization. Then we have also fitted our analysis, this magnetic resistance data with the equation calculated for the 2D square and hexagonal symmetry. So these are the AMR and PHE equations for square and hexagonal symmetry. Our experimental analysis shows very good fitting with these equations. So this is also in agreement with the theoretical analysis. Another, we have also fitted our data first at different magnetic field, first by the two-fold term, and then the residue was fitted with the four-fold component, and we see that it gets fitted with the four-fold component. Similar was observed for LVO-STU 111 case, that the data gets fitted with the 6-fold oscillation. So our this fitting analysis also suggests that they follow course 4, 5, 4, 6, 5 symmetry, which is expected for the square and 2D hexagonal symmetry, indicating that the AMR is the crystalline in our case. So here I come to the end of my talk. So I just conclude that we have realized the conducting interfaces of 001 and 111 oriented LVO-STU system, and these heterostructure shows 4-fold and 6-fold oscillations, and higher MR was observed for LVO-STU as compared to 111, and the origin of these AMR and PHE is the change in the Fermi surface because of the orbital polarization and hybridization.
Thank you very much. Are there any questions, please?
Shobna, can I ask a quick question? This is Arindam.
Yeah, I recognize your voice, Arindam. Please ask.
Thanks. So, Ruchi, what's the, I probably I probably missed the because of my bad connection. Do you know what is the electrical conductivity of these conducting surfaces?
That is around 3.1 into 10 to the power 14 centimeter minus 2.
Okay, and
Yeah.
did you try to gate these interfaces, or it just as grown? The data that you have shown is just
That is as grown, like under the application of magnetic field and the temperature effect we had seen. We have not applied any electrostatic gating and checked the effect of that gating.
Okay. Good. Thank you.
Any other questions?
Can I ask one?
Yeah,
Someone-
please do.
Yeah, so Ruchi, you said that by changing the stoichiometry, you're being able to make the interfaces conducting, right?
Yes.
So what was the thickness? I mean, and how are you changing the stoichiometry of lanthanum? I mean,
So those measurement was done on 50 monolayer of the LVO film. So here all the measurement was done on 50 monolayer of the film. But yes, to like have the
so you have kept the thickness the same, and you have changed the parameters to change the stoichiometry.
Yes. For this case, thickness was kept constant. That was 50 monolayer.
Okay.
By which method you grown the structure?
This is for 001 direction.
No, which method?
That is the pulse laser deposition system.
And all the, since you have grown many layers, layer by layer, so all the layers are having same orientation?
Yes. The substrate is in 001 direction, so it will take the orientation of 001 only.
How did you ensure that?
1 second, Ruchi, can you stop sharing, and you can also see perhaps the speaker. Yeah, please go ahead.
Yeah, so how did you ensure that all the layers are having same orientation?
So we have also checked the XRD of the thin films grown, and we calculated the lattice parameter. So actually, if you change the laser fluence of the film, that basically changes the film stoichiometry, and this changes the lattice parameter also.
Okay, thank you.
Are there any more questions? If not, let's thank Ruchi again for a very nice talk. I'd also like to thank all the speakers in this session for giving excellent talks, and also everybody kept time perfectly. So thank you very much. Thank you.
So thank you, Shobna, for chairing this session. So we close this session, and we'll be back at 3:45 for the next session. Thank you.